We've already talked about most of these terms before, but I just want to make sure that everybody knows what I mean when I use some of these terms that are parts of a radical. So the radical itself is the actual symbol here. And the part that is underneath the radical is typically referred to as the radicand. If it has a number out in front of it, then that would be a coefficient. And then finally, the small little floating number out there that we usually refer to with the n is called the index. And when we don't have a floating number out there, then it's the one that we're most typically familiar with, and that is a 2. So we are taking a square root if it doesn't tell us that it is a different n value or index. Keeping our definitions in mind, let's go ahead and talk about how to make sure that you have completely simplified a radical expression. So the first thing you want to make sure of is that the radicand has no perfect square factors other than 1. And technically, instead of perfect square, we should say perfect nth power, because we're no longer just talking about square roots, we're talking about third roots, fourth roots, fifth roots, and the powers that would go along with those, a third power, fourth power, fifth power, etc. The radicand, the part underneath the radical, also can't have any fractions. And the denominator of a fraction doesn't have a radical. So let's take a look at some examples. These will be similar to square roots, and in fact, we're going to start with a square root, something that you are most familiar with. So let's go ahead and look at simplifying negative square root of 20. Just to kind of reinforce that this is a square root, I'm going to go ahead and write the 2 there temporarily just to kind of keep that in mind. And remember that in order to break this down, we need to look at a factor tree. So we're going to look at 20 and the factors of 20. So we'll have 10 and 2 is a prime number, so I can stop. 10 can be broken down into 5 and 2, both of which are prime numbers, so I can stop here. Because I have a square root, I'm going to do what I've always done and look for pairs. However, as we move forward and we have something besides a square root, instead of looking for pairs, we are going to be looking for sets of whatever our index is. So I'm going to go ahead and explicitly write that we are looking for pairs or an index of 2. So make yourself a note that because we have an index equal to 2, we are looking for sets of 2. And this is what we're used to doing with our square roots that we've used this in the past. So I have a set of 2 2's, and then I want to identify that, well, 5 is kind of the everything else. So let's go ahead and rewrite this. I have my negative sign that I had before, and now I can pair up that set of 2's and say that that's the square root of 4, because 2 times 2 is 4. And then the everything else that I have left is 5, and it doesn't get to pair with anything. So let's simplify this now. The negative is still coming along for the ride. But I know what the square root of 4 is. I know that the square root of 4 is 2. And then the square root of 5, well, that's just going to have to stay square root of 5. So this is our final simplified form. We have pulled all of our perfect, in this case, square factors out of the radical. For this next example, notice that my index is 3. And so once we do our factor tree, we're going to be looking for sets of 3 to put together instead of sets of 2. So let's see what that looks like. I'm going to start with 135, and I'll break that down into, well, I know 5 will go into it, and that's 27 times. 5 is prime, but I can break 27 down into 3 and 9. 3 is prime. 9 breaks into 3 and 3. I'm looking for sets of 3, no longer pairs, because I have a third root as an index that I need to take care of. So there is a set of 3 3's, and I have this little leftover 5 again. So I can go ahead and rewrite this radical as the third root of 3 times 3 times 3. Well, that's 27. And then I have that little 5 left over, and it's still a third root as well. I know that the third root of 27 is 3. I just multiplied 3 3's together to get there. So I can rewrite that one and simplify it as a 3. And then we will still have that third root of 5 that we can't simplify further.